Hi, everyone. We're here to talk about Cassandra and response time sensitive environments. This is a talk that will describe Cassandra's specific behaviors, but for the people here that said response time sensitive environments are interesting, I'll be going through some examples of thinking in response time sensitive environments in general as well. This is a sponsored talk. So I will go a little bit beyond what I normally do in talks and bragging or talking about what we do as a company, but not entirely. So I like to keep my talks very technical, not just brochure-like. A little about me. I'm Gil Tene. I'm the CTO and one of the co-founders of Azul Systems. At Azul, we build Java virtual machines. It's all we do, and I've been there for 13 years now. So I've been working on Java virtual machines and interesting things around them for that long. One of the areas that you might have heard about the work we do is garbage collection. We think we've solved garbage collection, like truly solved it as far as servers are concerned. I know that sounds bold. You'll see some results here, but in general, you can find some other material about that. This is a little bit of evidence of me working on that problem. That's a trash compactor in my kitchen. The job of a trash compactor is to perform minor garbage collections during the week so that the full GC, where you actually have to take the bag out and go out in the dark and not trip on things, is only going to happen once a week. In this case, the compactor was broken. Fragments were coming out the back. The algorithm wasn't working quite right. So I figured I'd take out a book and take a picture with it. And this is starting to get a little old with the picture, but I've been thinking that's funny since 2004. So I've been working on GC that long, at least. I've built lots of things, not just garbage collectors, not just JVMs. I've built operating systems and drivers and helped design chips and instruction sets, real-time systems, switches, firewalls, routers, and then all the way up the stack to application servers. When we couldn't just buy WebLogic, we had to build our own because it didn't exist yet. And big applications that run, deal with millions of subscribers and nationwide kind of things when the web was just taking off. So I've learned a lot of bad habits and learned about some of how bad the habits are. I do like to go around depressing other people by showing them how bad their habits are, especially when it comes to understanding and measuring what they do. But that's a subject for a different talk. If you want, you can see one tomorrow. Tomorrow we actually have an entire track dedicated to depressing people. It's called Unlearning Performance Myths. And the criteria for each and every talk is that you will go out of there knowing less than you did coming in about something. So we'll see if that works, but that was at least how we chose the talks. As I said, it is sponsored, so I'll go a little beyond what I normally do. I'm from Azul Systems. At Azul, we build Java virtual machines. It's all that we do. We don't do anything else. And our JVMs have been powering all kinds of cool mission-critical bet-the-business things for over a decade now. So we think we know how to support them well in production and keep customers happy. A lot of our expertise has to do with latency and responsiveness. So a lot of times when people choose our products, it's because they want better responsiveness, better latency for some business reason, whether it's trading on Wall Street or online retail where just more people buy stuff if it doesn't annoy them. And Cassandra is one of our most common deployment scenarios for our products. In fact, it's between a quarter and a third of all deployed Zing nodes in the world today. And that's not because we have that many Cassandra customers. It's because Cassandra tends not to be small. So when somebody deploys it, they usually go very wide. Product-wise, we have a product called Zing. It's very simple. It's a JVM for Linux x86 environments. It focuses on delivering a continuously responsive environment as opposed to a sometimes very good between very terrible hiccups environment, which Java is known for. And we believe that we've done that. we've eliminated garbage collection as an issue at server level applications. When I say eliminate garbage collection as an issue, I mean that garbage collection artifacts are smaller than OS artifacts, therefore they're gone. It's not that they're gone in the actual academic perfectionist view, it's just that you can't measure them anymore. Operating range is very wide. We go all the way from low latency applications that measure things in low tens of microseconds and really have a cow when something takes 3 milliseconds, to large in-memory applications where people are kind of annoyed if they have to go out for a coffee, come back, and hope the garbage collection pause is over on their 300 gigabyte data queue. And the whole range in between, whether it's low allocation rates, high allocation rates, low throughput, it's an entire range. The idea is eliminate the problem, not shift it around, not tune for some size. And our approach to this is not that GC is the problem, it just happens to be the biggest problem. It's that anything where the computer stops executing for no good reason and has you wait for a while is wrong. So continuous execution, or not just sometimes fast, always fast, is the overall mantra of how we think about things. That absolutely affects design. So when we have trade-offs and choices to make, if we are facing an optimization that makes the average better but doubles the worst case, we don't like that. And unfortunately, most optimizations have that quality. Sometimes we fall into that trap too, but we try not to. What is this good for? If you've got a server-based application on Linux x86, and it has more than about 300 megabytes of data, not gigabytes, megabytes, then we're probably going to deliver better performance metrics, better behavior across the entire latency spectrum under load. Now, whether or not you need this depends. Maybe what you're doing right now is just fine, but if you do have a response time sensitive application and these artifacts are in your way, this is a simple way to address them. People use this for low latency, for machine-to-machine level latencies in the tens of milliseconds. For human response time, a lot of portals, a lot of retail, a lot of web, and then all the way to large in-memory applications for analysis, whether it's risk or ad placement or what have you. Very common there. So enough for the, this is Zing and this is what it's good for. Oh, well actually, sorry, not enough. Why Zing? This is the simple boss picture we usually use. A before-after picture. On the left you have regular hotspot running some sort of a cached application. On the right you have Zing running the same application. And then we say, look at how beautiful Zing is. It's beautiful not because of the shape of the lines, it's beautiful because of the scales. And you know, if we actually drew it to scale, it'll look like this. This is usually where we end up if we're trying to explain why Zing is good for something. Cassandra or other things, if we could show a picture like this at the end, it's kind of self-explanatory. When we look at measuring that kind of stuff, or when we're trying to figure out what response time behavior or sensitive applications want to behave like, it's very important to look at performance, including throughput, from the point of view of requirements. I like to define a term called sustainable throughput. And sustainable throughput is not how fast the machine can do. Sustainable throughput is how fast are you willing to let the machine go. The difference between how fast it could do and how fast you're willing to let it go is whether or not people are going to get very angry at you if you let it go faster than that. This is a good example of a speed you shouldn't go at. Okay? You can go that fast, but you probably don't want to go that fast unless you want big bills to pay as a result. And when we measure how fast transactions per second, for example, a single node or a cluster can do, the proper question is almost always, how fast can I run it without getting angry phone calls from someone? That usually determines how many machines you're going to buy or deploy on. The way to know that you need more machines is you start to get angry phone calls, or you think you will, right? You cannot run all of Google on this laptop, I think, right? The question of how many laptops is answered by determining sustainable performance for whatever that is. We'll come back to what that means later because a lot of the measurements I'll be showing you take this into account. Now, when we do look at responsiveness, we need some way to evaluate what is good, what is bad, what criteria do we need to hit. Obviously, you can just deploy and see if angry phone calls happen. That's not a bad way to do it if you're at scale and you can afford to play with things. But usually you try and estimate what causes those bad things. And percentiles are a very useful way of trying to look at that. Determining some level of responsiveness at some percentile. Usually a few of those steps are good for determining a service level expectation or agreement or contract of some sort. And when we look at that, people do intuitively tend to measure using percentiles. Unfortunately, I find that they tend to measure using the wrong part of the percentile spectrum. For example, most tools that you have probably measure all the way up to the 99 percentile. That sounds like a good big number because, hey, you covered 99% of the spectrum, right? Well, a common thing to try to understand is 99% a rare thing? Do I care about better than 99%, or should I just look at the main part of the spectrum? In order to understand why this really matters, in services in general, whether there's just a regular microservice, a web server, or a database server, is to remember that one operation on the thing that you're measuring your percentiles on is only a small part of what a human experiences at the end. And you're dealing with cumulative probabilities when you ask questions about what people experience. So for example, if we wanted to know what the chances of one web page seeing the 99th percentile latency of some server is, we'd need to do some math in between, because that server might be a search engine server, for example, one node. We'd like to measure them and monitor them. Or maybe a key value store, or a database in general, or a CDN node in Akamai somewhere. Now, each one of those is something we can measure these percentiles for. And we could look at the spectrum and say, look, the whole spectrum up to 99% is pretty good, and we know what the 99th percentile is, and we probably covered most of it. So I like to do actual math on these things, and these are actual web page lookups on the home page of each of these nodes a year ago. And what you have there is the number of individual HTTP requests that then individually translate to probably more than one low-level service request each. And how many of, basically how many of those requests there are. And then next to that is what the chances are of hitting the 99 percentile of those requests. What you can see there is pretty much every web page you will go to today will have a probably more than half, 1 in 2 chance of you seeing the 99 percentile in that one page. That's because of cumulative probabilities. The same applies if this was 20 database requests to satisfy one query and so on. Now, when we look at this, and I'm bringing it back to what you're watching, our monitoring tools can often show us a wide selection of numbers. And when I look at what we usually focus on, you'll often see people looking at percentiles on one side or another. For example, if you have something you can measure all the way to the 3 nines, that seems like near perfection, or just show you the 95th percentile, and you had to choose one metric to report on, one metric to put on your monitoring system or to tell your boss about, which one of those is better? Suppose you can't afford to show both. Which one should you choose? Well, which one is more representative of what your users will experience? If we do a similar set of math to what I did before and be a little more conservative. So let's assume a session involves only 5 clicks, and let's assume that each click is only involving 40 resources. Both of these are much smaller numbers than reality. Then what are the chances of a user not seeing something worse than the 95th percentile of whatever we're measuring? In this case, let's say worse than the 95th percentile of an HTTP request, or say worse than the 95th percentile of a database request. What are the chances of a person seeing no worse than this? Well, the chances are roughly that. And this often surprises people. I mean, 99.997 of people, of sessions, are going to experience worse than the 95th percentile of an individual server. Why are we watching this number? What's interesting about it? Other than it makes us feel good because we think we covered most of the spectrum. We haven't even scratched the beginning of the spectrum, right? Now, in contrast to that, if we looked at the 99.9 percentile, it's not perfect, but at least that one covers 18%. Like a whole 82% of people are actually going to be, affected by this. So it's a number that affects a lot more people. Therefore, if you had to choose which of your percents to look at, the higher percentiles are actually generally much more representative than the lower percentiles are. Don't fall into the trap of saying 90%, 99% and thinking that's of people. 99% of your Cassandra read request times are not what people see. Okay. So with that, I'm going to go into one more piece of background that is critical for understanding response time. And that's the difference between response time and service time in servers. Now, we can get into the definitions of response time and service time in queuing theory, but it's much easier to do that with a cup of coffee here. I just had one. This guy over here that takes an order and maybe makes a cup of coffee can be measured with service time. How long does it take that person to make a cup of coffee when requested? Response time is what that person at the end of the line sees. How long does it take to get a cup of coffee from this person? And the difference between the two is the length of the line and how quickly the line gets drawn, right? They're very, very different numbers. If this person goes out to lunch and forgets to have a replacement, when he comes back, we're going to measure the service time and say, you know what, this one cup of coffee took an hour. But now everything's fine again, so we had one bad cup of coffee. That would not reflect the fact that there might be a line around the block as a result, and it takes a really long time to get a cup of coffee here for a while after this, right? Now, to depict this from a point of view of measurement systems and looking at behavior on a server comparing response time and service time, let's look at the behavior on a server on the two sides of saturation. I specifically chose these two throughputs. This is a Cassandra server. And this Cassandra server saturates for this operation at 87,000 things a second. It cannot do more, okay? On the left, we have the service time plotted, both by percentile and over time, for how long it takes to do that read request inside the server, both at 90 and at 80. And they're not very different. I can't tell the difference between them, okay? Because it takes the same amount of time to do a read request when you're saturated and when you're not. They're not different. But when we look at it from a response time point of view, they look very different. This is not to scale. I'll show you to scale in a second. At saturation on the left, there's a very interesting behavior to response time. Response time at saturation grows with time. It's not a level. Why? Well, I'm trying to do 90,000 things a second. That's my arrival rate. And I'm only completing 87,000 things a second. So 3,000 things a second accumulate every second. 3,000 more things. By the end of a 250-second run, I've got a lot of things accumulated. In this specific case, I'm 8 seconds behind. It'll take me 8 seconds to draw that line down if I stopped. The longer I go, the longer the line gets, because we're just not serving it fast enough. That is the behavior when you cross saturation. Now, when you have a load generator that doesn't show that, it's the load generator that is wrong, not the server that is actually performing 90,000 things a second, okay, or keeping response time good there. Now, before saturation, close to saturation, you'll see response time kind of do this behavior where it'll jump up and down because you have bursts and something slows down and you fall behind a little, but it's able to draw down. It's faster. The server is able to handle this load. So as noisy as it gets, it'll stay at some level, right, around some level. And here is that drawn to scale. I zoomed in before just so you could see that there's noise but a level, right? The level is obviously much lower than if you saturate it. This is all background for what we're going to actually compare in a second. And then there's one more thing we need to touch on, and that is this notion that I hear a lot about Cassandra. This is the coordinator is going to save us. The coordinator really helps dampen out individual node responsiveness issues. And obviously, if you don't do use the all for consistency, if you use quorum level consistency, which is pretty good. The theory goes something like this. If one node in my cluster pauses, the chances that other nodes in the same cluster pause at the same time are pretty low. And that is absolutely true. Unless we actually start coordinating our pause time, your likelihood of two nodes pausing at the same time is pretty much the the inverse, or the, basically you have a lower likelihood. If it's 99%, 1% to pause 1, it's 0.01% to pause 2. As a result, we're hoping that a quorum will be reached without that one node needing to come in, and therefore the client won't actually see the latency of that node, right? We have a pause, but it's masked because the other guys are going to answer. And this is sort of how a quorum read works. Same goes for a write, but we're going to look at a read here. A client talks to some node that's a coordinator, and the coordinator is going to send requests to multiple different nodes. Not all of them have to come back, right? It's enough for 2 of these 3 to come back for us to get that. So for example, if this guy paused, the client won't see the pause, right? This is absolutely true, by the way. Unfortunately, it doesn't help us at all, because what happens if this guy pauses? If that guy pauses, all the clients that talk to him are going to see the pause. And guess what? Every single node is a coordinator. So every single node is going to impact coordinator latencies. The fact that downstream we might be redundant doesn't help us against the fact that, hey, one node is a single pause point here. If the client was striping directly across multiple nodes, that might work against that and help bypass it. And there are some architectures, not Cassandra, but others, that will do that with some idempotent behaviors. But specifically in Cassandra, the behavior of one node is directly affecting the behavior of what clients see. You don't get to dampen it with other filters. Okay? It's not much worse. That's the good news. If you're running quorum level consistency, then you're not worse than this. You're just not better. If you required all 3 to come in, then you're more exposed than just the chances of one node. Actually, any one node in the 3 will cause it to happen, so you're 3 times as likely to see your glitches. Now, when I go and look at behavior of Cassandra specifically on Zing, because we focus a lot on eliminating noise, we start with the simple theory that Cassandra is affected by garbage collection. How many of you have actually had to tune garbage collection in Cassandra? Not a lot. So you use the default settings? By the way, the default settings from DataStax are pretty good. I mean, they've spent a lot of effort on tuning them, right? So here's a run with those default settings under a load, an example load from DataStax, actually. This is a mixed workload. And what I'm plotting here is simply the maximum response time in any 1 second, plotted over time over about 10 minutes. This is regular hotspot running Cassandra. And at the bottom here, by the way, you're seeing both the response time and the service time reported. This is Cassandra stress, but a slightly enhanced one. This is Cassandra stress that measures both response time and service time. Unfortunately, the regular Cassandra stress only measures service time, which is why I highlighted the difference between them. You can see the differences in numbers there. At the maximum, they're kind of the same, but at the other percentiles, they're a little different. I don't know if you could see into those numbers from back there, but for example, at the 95th percentile, there's a 240x difference between the two, which is kind of big. Now, this is regular hotspot. Here's Zing for the same work with its same measurements. Here's the 2 of them side by side. Here's the 2 of them with Zing drawn to scale so that you'll actually have the same y-axis scale. Now, as I said, we have this hypothesis that Cassandra responsiveness is affected by garbage collection. This is the simple visual proof of that, not by looking at GC logs or trying to figure out behavior. It's really simple. The only thing Zing improves here is garbage collection. All we did is improve GC pause times and dramatically reduce them. And if that translated into measured, dramatically lower responsiveness or response times on Cassandra, that simply proves that all those red spikes were garbage collection related. They're not necessarily the pause itself. It may be the impact of queuing after the pause, that long response time happening. Now, you will see that there's a glitch there on Zing too. There's a spike, and that spike is actually about 20 times as big as any GC pause. That spike is some queuing behavior as a result of something that slowed down. In this specific case, that's a compaction event that slowed down throughput temporarily and caused queuing. So this happens. Zing will be just as susceptible to queuing behavior if it happens as anything else. It just happens at a higher rate or a smaller queue, whatever it is you want to call it. So this is simply a way of looking at it from the outside. If we take away GC pauses, do things get better? And the answer is yes. Okay. And I'm going at it from the proof backwards rather than trying to explain why it might be so. Now, at that point, I will often get a lot of questions from people that do a lot of hands-on Cassandra in high throughput and response time sensitive environments, and they'll say, well, my picture isn't that bad. I don't have 1 second pauses every 2 minutes. I've tuned it so it's a lot more rare than that. I'm interested in the in-between. So the rest of what I will show you focuses on that world. This is a world where somebody's done a lot of work to get rid of the large pauses, and they're only left with the little pauses, the tens of milliseconds as opposed to the hundreds of milliseconds. Note, this is not the real world. It's the world of a highly tuned, very fine setup. And what I did here is run a specific set of experiments focused on that, on that problem. So I aimed at repeatable results, meaning if I wasn't able to repeat the same test multiple times and get very similar results, I threw the test out. So for example, if I did have a large GC pause inside of it for hotspot, I threw the test out. This is only new gens, right? There are no old gens involved. And it's a read-only test, which really helps with repeatable results. So this is a database populated with a fixed set of population, and then a read done of the same database. It really helps the ease of testing, right? Because you're not mutating the data, repeatable testing is easier. So I did it mostly because I'm lazy, but it's also a good way of demonstrating at the lower end of the spectrum in a nearly perfect workload how good can get if you eliminate GC pauses there too. This all was run on Cassandra on AWS, by the way. This is a, oh, what did I just do? Oh, there. Oh, there's a button here that turns off the screen. Great. I don't have one of those on my clicker. So it's run on AWS. I ran it on a huge instance on AWS. This is a 32 CPU, 244 gigabyte node on AWS. I didn't run it on that because I needed it. I ran it on that because that makes things repeatable and quiet. If on AWS, if you sit on a machine that big, you tend not to have neighbors. And not having neighbors tends to help with the noise of measurements at the milliseconds and tens of milliseconds levels. And I can share the details of this later if people want. Now this is the test I mentioned before that saturates at 87,000 reads a second. That's the rate at which we can't go any faster. And I'm going to go through a set of measurements that I collected for this and explain my thinking of going through the measurements and how I compare things. Okay? So let's start off with measuring it on the two sides of saturation, 90,000 and 85,000. As I said, it saturates at 87. And it saturates at 87 roughly for both Zing and Hotspot. We're not actually different there. Zing is a tiny bit faster here, but that's not material. And we could look at this set of results and say, hey, look, in this case, Zing is the blue line and Hotspot is the red line. Look at how much better Zing is. I mean, it's half as bad everywhere, and it's extending, into the median better, and everything's better here. That's for the 90s. And the 85s are down there, the green and yellow. Well, that's the wrong place to compare things. What I just did is compare the shape of the bumper of two red cars that ran into poles. It's great that Zing is better. It doesn't matter that it's better. You're never going to run at that speed. You shouldn't be running at that speed. This is not the right place to compare things. The only value of looking at a chart like this is to know that you shouldn't test there. This is too fast. And what this is really telling us is don't look at 90. Let's look at 85. Okay? So I'm not going to jump into the, I'm not going to succumb to the temptation to go start analyzing the red and blue lines here. And then to repeat a test with different metrics and different little tweaks to try and make the shapes better. That's saturation. It's going to be bad. In fact, if I double the test length, the height would double because it's saturation. So if we zoom just at the 85s, we start seeing a little more of a spectrum and a little more of a comparison. By the way, the colors unfortunately alternated in my charts because I couldn't control them well. Here, red is Zing. Now I could also look at this and say, look, Zing is better across the spectrum. Look at how cool it is. But again, This is 85,000 things a second in a machine that can only do 87,000. It's great that we're a little bit better there. You shouldn't run there. Nobody in production that cares about responsiveness should run anywhere close to this throughput. And you're basically being told that by seeing that the lines bend at the 90% or below, and you really, really don't want to be anywhere near this. So let's look at slower. I'm going to cut to half the speed of saturation, or a little less, at 40,000. Remember this 87,000 saturation. At 40,000, I've got something that goes to the 95% plus with almost flat responsiveness, and then starts showing behavior above that that varies between runtimes. And it's not a surprise that the behavior below that is virtually identical. No magic there, right? Now, at this level, I could say, you know what? Zing is better. That red line has a lower 99 and 99.9, etc. So at any given point, I could pretty much say my percentiles are better than this. If I start doing the cumulative math to what that means to actual requests and actual humans, it'll be good. But usually that's hard to project from. It's hard to sell. Because it's not quite clear, like, okay, good, so I'll get more responses at the 5 millisecond or 10 millisecond level instead of the 20 and 40. How bad, do I really care about this? What can I do with that? What can I actually do with this to change the way I deploy or configure? So if your problem was you were really trying to get down to that line, there are more ways to get there than just running Zing. There's a really simple way to get there, and that's to run less load. Right? How many machines do you need is one of the things we can change with this question. So for example, I could ask, I could say something like, well, the 99 percentile for Zing here is pretty good, and the 99 percentile for hotspot at 40,000 a second is not that good. How slow do I need to run hotspot for me to be happy? So for example, I said I want a 99 percentile of no more than 5 milliseconds for this Cassandra server. Here, I just did that. I slowed down hotspot and met the requirement. See that? And that's fair. That's allowed. That's good. That's exactly what capacity planning is supposed to be. Let's slow it down and see if it fits the shape I need to. And if I just cared about, that level, the 99 percentile, now they're almost identical there, but at different rates. This is what I use to show people that if you cared about a 99 percentile of 5 milliseconds for this workload, then Zing can carry 4 times the load doing that. 4 times before it cracks, right? At 80,000, it was much worse than this. But at 40, it can do that, and it takes hotspot. You need to slow down hotspot to 10K a second before you get that level of quality. We could take this further and say, well, 99 is nice, but 99 is what everybody sees, right? What if I wanted to go further on the right here? Let's say I want to get a 99.9% that is better than 10 milliseconds. Now, Zing is sort of skirting with that 10 millisecond line there, and that should make you a little nervous. So let's slow down Zing and hotspot to meet that. And now they're both below that 10 millisecond mark. Now, I slowed them down, right? The rates are now much slower. Zing is down to 20,000 a second. Hotspot is down to 2,000 a second. Now I can tell you that if you care about the 3 nines being 10 milliseconds or better on this workload, Zing can carry 10 times the load before that happens. Remember, the machine is the same machine. The saturation load is the same saturation load. But how far you can run before response time starts sucking is what we're measuring. Now, we could do a lot of other comparisons. The nice thing in repeatable tests, and this is actually my criteria for repeatable test, is that you can, if you vary your load, you should see some sort of logical progression of behavior. This is hotspot plotted on everything from 2,000 operations a second to 80,000 operations a second. And you could sort of see this interesting progression between them. In fact, this 80,000 is clearly outside of the normal behavior or response to load, right? There's this range that we could naively call the linear range, right? More load just shifts it, one or less load shifts it a little bit to the right and left, but we can sort of see the same shape. It's not actually linear, but it's the sort of predictable operating range. It's how it's reacting to load. And then there's this thing that just completely separates from it. What that's telling you is just don't run here. This is the past the beginning of the knee kind of behavior. It's the area where you're not yet saturated, but you're hypersensitive. So again, don't run here. That's 70, that's 80. Stay at 70 or below. That's what that's telling you if you're just looking at hotspot. Now you can run that's just focusing on that range. We can look at Zing for a similar set and try and put them next to each other. You could do all kinds of nice comparisons. By the way, there are good tools for doing all this if you want to repeat that later. And there's some good plotting tools for doing this online. And we can even put them next to each other because they're nicely separated and highlight kind of that behavior grouping. So with this chart, instead of saying something like, I can carry this much more load at a given SLA, we could reverse the question and say, how many angry phone calls am I going to get today at some load, right? So you could basically say at any of these loads, Zing has 100x less bad occurrences at a given point. Let me explain why. This, for example, this line right here is Zing running at 60K, 60,000 a second. This green line is hotspot running at 60,000 a second. They're about 2 orders of magnitude apart on the percentiles. And that's true for the other ones too. So if you're asking how often will I get this magnitude of event, it's 100 times less likely on this setup than in that for the same load. That's a way to compare it, cross-cutting from the how often are things going to be bad, how many timeouts per minute will I have, that kind of stuff. Okay, a few other ways to chart these, and note I'm just throwing charts at you as ways to look at data, because I actually think that these visuals are probably the most key thing for you to take away is how to compare two things, whether the two things are Zing and hotspot running Cassandra, or Cassandra at speed A or speed B, or Cassandra with your cool new tuning that you came up with on the weekend because you want a bonus tomorrow and you want to brag, and this is how you brag, right? So this is your bragging setup versus the previous setup, same load, right? And this is a similar comparison to what I showed before. This is a timeline behavior. And when you turn this into something you show a CFO or a CEO, these are much more readable to them than these. So it's just which one do you want to run on? Which one looks better if each one of these was a glitch, right? So at a given load, you can compare them, or you can compare them at high loads, again, near saturation, or you can compare them at the different loads, right? This is 10K, that's 40K, carrying 4 times the load and still clearly happier. And you could do that again with the 20K and 2K, the same thing. So at 10 times the load and similarly happy, I would say. So, the differences are all there. Now, remember I told you that we start off with the simple proof point of those red spikes are caused by GC, not because I need to find a GC log that shows it, but by simply showing that if the GC problem go away, which is all Zing did here, then the problems go away. And our simple boss chart for that ends up just being this, So you can run Cassandra on hotspot, which works just fine. But if you want better responsiveness, you can run it on Zing, and it'll just be happier. And that's usually all we do to explain to people why Zing is good for Cassandra. That's about it. Now with this, I have the any questions part. We could do a lot of Q&A, and we do have some time for that. Good. So I'd like to open it for questions from the audience and see what specifics people might want to know about here. There's back there.
What's the garbage collection algorithm that you use with hotspot?
So the question was what the garbage collection algorithm with hotspot was. This was CMS on an 8 GB heap tuned with the DataStax recommended setting for the test. This is not G1. I tested with G1 and it was worse, so I showed CMS. At least for these set of read tests, the outliers were much higher for that. So that's the answer there. For Zing, this is just the default configuration for Zing on the same setup, on the same everything. No tuning. Yes?
Do you need to tune Zing JVM as you tune hotspot?
Question is, do we need to tune the Zing JVM as you tune hotspot? No. I can't say that there is zero tuning on Zing, but it's sure close to that. The main tuning knob for Zing is how big of a heap do you want or need. And Zing gets happier with bigger and bigger heaps. Or more specifically, the garbage collector works less and less the more heap you give it. And it doesn't change anything in its pause time or responsiveness behavior. So a way to, say, improve throughput is to give it more heap. There are a few other tunables, like how many threads you allow the GC to have. But there's nothing near the kind of tuning that you might be used for from other collectors. Just basically one big knob.
Does Zing run on a stock Linux, or do you need some patches or modules?
Question is, the reason I'm repeating the questions, by the way, is for the camera. The question was, does Zing run on stock Linux, or do you need some sort of specific patches or kernels? It runs on stock Linux, or pretty much on all the regular Linuxes that people have. So that includes Red Hat and CentOS and Scientific Linux and Ubuntu and Debian and I forget a few other, Oracle Linux. So Zing as a product does have a system level component. We call it a ZST, it's Zing System Tools. And we do produce those for various operating systems, but we cover a very wide range, including the ability for people to, when they have custom kernels, to self-build for them.
Are there any recommendations for, in the proportion of CPU to the minor GC where we need to set and the major GC that we need to set?
So the question was, are there recommendations with proportion to minor GC and CPU and major GC and CPU and where you want to be? I would answer that separately for Zing and Hotspot. I do entire talks on garbage collection, not just in Zing, but how garbage collectors work. In general, if you spend a lot of your time in stop-the-world pauses, that's an issue. So your first goal when you're looking at responsiveness should not be to reduce the amount of CPU spent on GC, but the amount of time spent in pauses. Those are two different things. Because it doesn't really help you much that you have a lot of CPU empty if you're not willing to push the server hard. You kind of wish you could make the CPUs burn more and have better responsiveness, but you don't. So your goal, first of all, should be responsiveness, at least in this context. Within that, you will probably find that with a stop-the-world garbage collector like Hotspot, reducing the size and frequency of young gen pauses will help with that, right? And there are tricks that you can play with to do that. Unfortunately, often there's, well, if you do this, you do one. If you do this, you do the other. To give you a specific example, if you increase the new gen size in Hotspot, you will decrease the rate at which new gen runs. For every doubling in the new gen, given the same workload, you'll new gen half as often. Right? You only run the new gen collector when you run out of new gen. So if it's double the size, the same thing will happen half as often, and that same thing will be generally of the same size. So this is good. It's less CPU, it's less frequent pauses. So what's the downside of this? Well, unfortunately, the worst case behavior for the new gen collector happens when you have a lot of new gen stuff that doesn't die. Usually they die very quickly, but sometimes, every once in a while, you have a lot of things in new gen that stay alive and get promoted. And the size of the pause involved is linear to the size of the new gen. Double the new gen, double the number of things that will be promoted in a single pause, double the length of the new gen. Well, what kind of things are we talking about? In normal application behavior, most of your stuff dies young most of the time. That's absolutely true. The things that tend to negate that are phase shifts in application behavior. For example, flushing a cache, compacting Cassandra, or any of those things that cause a transition in your data sets where suddenly you're loading a lot of new data and it's not dying, it's making it into your surviving metadata. At that point, you're going to have a large new gen pause associated with it. So the larger your new gen, the larger your bad pauses are. It is better for throughput, it's better for averages, it's better for service time averages, but response time might get worse. Now, all-gen it's a more complicated subject that maybe we shouldn't get into here as another talk. Switching on the Zing side, the answer becomes you just don't care. There's only one thing you watch with Zing, and that's how busy the collector is. And the collector has a new gen and an old gen, but they're kind of self-pacing, and the whole heap belongs to both of them, and you no longer care about the differences. What you do care about is how busy is the collector. Not how much CPU it's using, but how busy is it. Why do you care? Because if the collector is working nonstop, you should be worried. There is some rate where you're going so fast, the collector can't keep up with you and produce empty memory, at which point even Zing will cause a pause. The good news is, before that happens, you will see the collector be busy nonstop. So that's the thing you're trying to prevent. Most people will tune the heap size on Zing to keep the collector from being busy all the time. They like to keep it at 5 or 10 or something like that % of the time, wall clock time. And if the collector is idle 90% of the time, it's got absolutely nothing to do, you could be very comfortable. It can handle 10 times the load spikes and still keep you concurrent and nice and not pausing. That's usually the approach on Zing. You stop looking at the part of time that you pause because they don't exist, and you look at how hard is the collector working to keep up with you, and should I be worried that it's on the verge of not keeping up? And your goal is generally to just make it very, very happy and very calm, and that's pretty easy. Just throw empty memory at it. Works. Thanks. Yeah.
My question is about hardware. So you chose the biggest available capacity. Does the behavior changes when you load down the spec and you have a bigger number of very low spec hosts and you run at lower speed?
So I'll repeat the question. Hopefully I remember the whole thing. The question was about hardware. In my example, I used a very large instance that wasn't completely utilized. Does the behavior change if you run on smaller, more right-sized kind of hardware pieces and a lot of them? And the answer is, at some point, yes, it will, right? If I run a lot of 2-core, 12 gigabyte things, it probably will get squeezed more than this. In this specific set of tests that I ran, out of 32 cores, the most CPU that was used at saturation was around 12 cores. And that's at saturation. Now remember that the point at which you would be willing to run on those boxes was, we measured from half down, right? So from 6 cores down to maybe 2 cores of actual CPU used before response time starts cracking your limits. So in all the tests I showed here, we weren't using a lot of cores at the rates we were measuring, right? In fact, if you had, probably on hotspot, if you had fewer cores, then the pauses would have been bigger. Because when the GC happened, it had 32 cores to use to do that NewGen fast. If it only had 8, it would have taken longer. But if we discount that, most of our tests here, and I actually think this is true for most of production deployments of Cassandra, tend to run at a low CPU utilization, at a small percentage of the CPU available on the machine, or more like at a CPU utilization or filling up a handful of cores before response time behavior starts cracking what you do. The heap size tends to follow that a little bit, although my understanding, I'm in no way a Cassandra tuning expert. I mostly just play with what other people give me and then try and beat it with no tuning. I'm happy when I can. An 8 gigabyte heap size for Cassandra seems to be sort of a sweet spot recommended level for anybody with throughput sensitivity and response time sensitivity as well. It's kind of, okay, do this, we've tuned it, we've played with the settings. There might be new ones from DataStax that'll come up. People tend not to push larger than that because of other effects. And as a result, you usually see instances with, you know, say 16 gigabytes or 32 gigabytes of memory, file cache needs space. And no more than 8 or 12 or 16 cores, and then replicate. There's nothing wrong with that. That's a good way to go. Zing will probably fit into the exact same nodes pretty well, but you often do find that with Zing that more memory is good. So more heap is good, more memory for the file cache obviously is good. And since you can actually squeeze more throughput out of that node, you can afford to do that sometimes, right? So can you squeeze more throughput out of the same small nodes? Probably yes, but very often what we'll see is people will go to, say, nodes that are slightly larger and many, many fewer of them for the same SLA. Yeah?
If you were only using a fraction of your CPUs, then what resource or subsystem in the machine was saturated or locked or whatever that was making 87,000 VRAMs?
So the question was, if it wasn't the CPU, then what caused saturation? Let's say, I mean, we could take these charts, for example. I mean, both of these were affected. The answer is I actually don't know. I pushed until it cracked. I pushed to saturation and it wouldn't do more. If I had to guess, it's probably the way I configured the SSDs or something. But I don't actually know. I'm pretty sure the network wasn't saturated at this. I've seen single nodes do more than that from a request per second point of view. But I don't know. And I didn't try to identify that in this case. Remember, this is the saturation level. Most of these tests were focused on reach saturation and go way below to see what's happy in there. Okay, we're being asked to stop. So if people do want more details, I'll hang around outside for a little while, and I'll be happy to chat. But thank you all for coming, and please come to the track tomorrow. I'm the track host, so it's my job to solicit people to come. Thank you.